Hi everyone, I want to do a little tutorial on how to handle some of these blood pressure and blood acidity regulation questions. There's definitely going to be a couple on the exam, and it's a little bit trickier to think your way through it. So anytime we're talking about the regulation of blood pressure, I like to draw a little kind of sample blood vessel just to help my mind think about it. And imagine you've got some blood in this blood vessel. Right, so here we go. This is some sort of vessel of some kind. Well, according to various laws of physics, there's two ways that you can change the pressure inside this vessel. One is by decreasing or increasing how much volume is in the vessel. All right, so imagine two scenarios. One where this vessel is the exact same size, but in one scenario it has hardly any fluid at all in it, and in the other scenario it's got tons and tons and tons of fluid in it. And that if the size hasn't changed at all, you can imagine that increasing the amount of volume while keeping the size of the vessel the same would actually increase the pressure, right? If you try and fit more stuff into a confined space, it builds the pressure. So the first way that you would alter blood pressure is, all that to say, affect cardiac output, okay? Because cardiac output is really going to be what's going to determine how much fluid is in that vessel, because when the heart ejects blood, that blood goes into the vessels. Another thing that can happen, though, to reduce or increase the pressure in here is to change the size of the vessel. So you could either increase or decrease the size of the vessel. And this is going to get to this idea of resistance. The more you shrink a vessel, the more resistance it has, meaning it's harder for stuff to get through it, and that also is going to increase the pressure. So size. Okay, sorry, let me say that again. So now, considering size, you can either increase or decrease cardiac output, or increase or decrease the size. Imagine two scenarios where you have one vessel that has the same amount of fluid now, but one of the vessels is really huge and one of the vessels is really small. Well, the one, if you've got this much fluid and you've got a vessel that's this small versus that same amount of fluid in a vessel that's really, really big, okay? Well, there's going to be less pressure in the huge vessel because there's more space for that fluid to move around. All that to say, if you increase the size, it will lead to a decrease in pressure. If you decrease the size, it will lead to an increase in pressure. And that's different than over here. If I increase the cardiac output, that's going to increase the pressure. If I decrease the cardiac output, it's going to decrease the pressure. Okay. All right. So now, keeping that in mind, let's take a look at these different scenarios. So I'm going to draw this so you can see it better. The question is asking which of the following scenarios are going to reduce blood pressure. So, and there's going to be multiple of them here, so you can choose whichever one is correct. So the first one says the inhibition of the cardioacceleratory center. Okay, so the first thing you have to try and decide is if we're talking about which one of these, changing cardiac output or changing size would be the effect here of the cardioacceleratory center. And part of that requires that you actually know what the cardioacceleratory center is. Okay, so to do these questions, you do have to have a little bit of background knowledge in what these structures are. But at any rate, the cardioacceleratory center, one of the things that it does is it increases heart rate. Okay, this is that center that's in the medulla oblongata. It's going to increase heart rate. And all the while, you have to keep in mind that cardiac output is going to be determined by heart rate times the stroke volume. This is our famous question, our famous equation here. So basically this inhibition of the cardiac acceleratory is going to affect heart rate. So if it affects heart rate, that's going to affect the cardiac output, because how much blood the heart is pumping, it basically relies on two things: how fast it's beating and how much blood it releases after each beat. Okay. So let's take a look at what this effect would be. The cardiac acceleratory center usually increases the heart rate. You can see the word acceleratory, meaning it's increasing the heart rate. But the questions, or the scenarios, that cardiac acceleratory center is actually being inhibited. So the net effect is to decrease kind of the accelerating function of the heart, so really what this means is that we're having a net result of a decrease in heart rate. Now, how is that going to affect blood pressure? Well, we'll come down here. It's not going to affect the size at all, but it is going to affect the cardiac output, because we're decreasing the heart rate. And so if we decrease the heart rate, assuming we keep everything else equal, that's going to lead to a decrease in cardiac output. And we said earlier, if you decrease how much blood is going into these vessels, it should decrease the amount of pressure, right? Because remember, two scenarios: one where you have tons of fluid in the same amount of space, and one where you don't have any fluid at all in the same amount of space. Well, the one with less fluid is going to have less pressure. So to decrease cardiac output is going to decrease the blood pressure. And since we are looking for anything that reduces blood pressure, and we just found that A decreases the heart rate, which according to this equation decreases cardiac output, which is something that decreases blood pressure, this is going to be one of the things that decreases blood pressure. Okay, now let's look at a different one here. Vasoconstriction. Vasoconstriction means that the vessel is getting smaller in diameter. And so which one of these methods of blood pressure is that going to affect? Well, it's going to affect the size, right? And so remember, we said if we shrink a vessel, it increases the pressure, whereas if you increase the size of a vessel, it's going to decrease the pressure. So this is saying we're shrinking the vessel, so that's actually going to increase the pressure. So this is not going to help us reduce blood pressure. This next one, increased natriuretic peptide secretion. Well, the first thing you have to know is what this does, and this is a diuretic, and diuretics make you lose fluid, okay? And if you're perpetually losing fluid, that means that the way that's lost is that it's you lose it in the urinary system, which we're going to talk about how that works later. But if you're losing fluid, basically what you're doing is you're losing the venous return to the heart. So here's your heart. Every time the blood goes out and then goes and comes back to the heart, if fluid is perpetually lost out of the vessels, then you're not going to be able to have as much fluid returning to the heart. And so keeping that in mind, remember when we talked about cardiac output equals heart rate times stroke volume? Well, one of the things that affects stroke volume is that venous return. And if you remember all of those factors that affect stroke volume, if you decrease the venous return, it's actually going to decrease the stroke volume, both because the ventricles won't fill as much, and also just because there's not a, then that's going to affect the preload, and it's also going to affect, the contractility of the ventricle. All that to say, if you decrease the venous return, decreasing the stroke volume, which is going to be a decrease in cardiac output. Now, again, would a decrease in cardiac output, how would that affect the blood pressure in the vessels? Well, remember we said if you decrease how much fluid is going in there, it's going to decrease blood pressure. So this will help to reduce blood pressure. Basically, this is a substance that the heart is able to release if it needs to lower blood pressure. Okay, the chemoreceptors are stimulated. This one I originally put in here just to throw you off. The chemoreceptors mostly are responsible for detecting pH, but this one's a little bit tricky because when the chemoreceptors are stimulated, they actually do cause some effects on blood pressure because they affect the cardioacceleratory center. But even still, one of the things, when they're stimulated, the chemoreceptors are actually going to cause everything to speed up. They're going to cause blood pressure to increase and cardiac output to increase. And neither of those would help to reduce blood pressure. So we'll cross this one out. And then lastly, the baroreceptors are stimulated. Baroreceptors are receptors that respond to pressure. And basically, if there's a high blood pressure, it pushes on those baroreceptors, and then they send signals to the brain that cause the brain to send all sorts of stuff out in order to lower blood pressure, right? Because it would seem appropriate that if there's high blood pressure stimulating those baroreceptors, then the body is going to work to try and lower blood pressure. So without even thinking about all the physiological effects of this, you can probably say it's safe to say that this would help to reduce blood pressure. And the way that it does is it actually, one of the very effects of stimulating blood pressure is to inhibit cardioacceleratory centers. So these two are kind of the same. And you'll often find that in these types of questions that some of the answer choices result in the same effect. Okay. Now on an exam, I'm not going to provide multiple answers that could be right. I'll usually just have one answer that you have to select that's correct. Okay, so if you can just eliminate all of the others but the right one, then you know you've got the right answer. All right, let's try this next one here. Which of the following occurs to increase cardiac output? Okay, so this is going to be related again to our heart rate times stroke volume equals cardiac output equation. We said that decreased venous return actually decreases the cardiac output. Stimulation of the baroreceptors. This, remember, is going to, let's take a look. This is going to work to lower blood pressure. Okay, so if I'm trying to lower blood pressure, what would the effect on cardiac output be? So let me draw my vessel again. If we're lowering blood pressure, that means we are either increasing the size of this vessel, or we are decreasing the amount of flow going into it, right? Either one of those things, decreasing the flow going in or increasing the size, either one of those things are going to lower blood pressure. But decreasing the amount of volume going there would be a decrease in cardiac output, and we're looking for something that would increase, so I can go ahead and cross this one out. All right. Now let's take a look at the next one. Decreased secretion of acetylcholine. Well, what is acetylcholine? You have to know what acetylcholine is to be able to assess this one. And acetylcholine is released by the parasympathetic nerves, which are controlled by the cardioinhibitory center, and its main job is to lower heart rate. Okay, so if your heart's going too fast, the parasympathetic neurons originating from the cardioinhibitory center, not the cardioacceleratory center, but the cardioinhibitory center, they can release acetylcholine to decrease heart rate. But again, this is tricky because it's telling us that we're decreasing the effect of acetylcholine. So we're decreasing the effect that acetylcholine has on lowering the heart rate, which means we're actually increasing the heart rate in the end. Okay. Now, knowing what we know about our heart rate times stroke volume equals cardiac output, if I increase the heart rate, holding all things equal, that has to be an increase in cardiac output, right? You can't increase one side of an equation without there being the equivalent increase in the other side of the equation. So this is going to help me increase my cardiac output. All right, and then let's take a look at these others and see if there's any others that apply here. Vasoconstriction. This is going to get to this idea of total peripheral resistance. So again, I'm going to draw my blood vessel here. Here's my nice little blood vessel. Vasoconstriction would be if I decreased the size of that vessel. And holding all things equal, the same amount of energy and everything else, if I decrease the size of that vessel, I'm actually increasing the resistance. And when you increase the resistance, you're basically making it harder for stuff to flow through it. And so this is actually going to make it harder for the heart to push blood through, which means you may have less cardiac output, because given this, we're not told that the heart is that the heart is doing stuff to match this increase in resistance. We're just assuming that the resistance has been increased, and holding all things equivalent, what is that going to affect? How is that going to affect the cardiac output? And the answer would be to decrease it, because basically you're making it harder for blood to pass through this vessel if you've decreased the diameter. And then if it's harder for blood to pass through, given the same amount of energy, you're not going to have as much cardiac output. And this has to do with the, when we think about this equation, this has to do with the afterload pressure. Think of the heart and think of the aorta coming off of the heart. Well, if I vasoconstrict, basically I'm making it harder. I'm basically increasing the afterload. You're increasing the amount of pressure that's in this vessel. And so, as we said earlier, the heart has to work harder to overcome the afterload pressure, so that once it finally does, and the aortic valve opens, or the pulmonary semilunar valve opens, then because most of that energy was spent overcoming the afterload pressure, then there's not going to be as much left to push it out. Okay, so all that to say, vasoconstriction generally is going to lead, holding all things equal, to a decrease in stroke volume, which would mean a decrease in cardiac output. So we're not going to think that this would increase the cardiac output. Increased fluid loss. Okay, this goes right back to this other question. Remember, natriuretic peptide is the loss of fluid. We're not told that the reason the fluid loss is due to natriuretic peptide, but the effect would be the same. And let's see, can you remember what the effect was? You decrease the fluid. Let me just clear out this up here so you don't get too cluttered. If you decrease fluid, you basically decrease venous return to the heart. If again, this is my heart, and let's say this is the cycle where blood goes out to either the body or the lungs and then comes back to the heart. If you're always losing fluid out of there, then that means the amount of fluid coming back in is going to be less. It means the heart's going to fill less, which means it's not going to have as much preload pressure, which means that the contractility is not going to be as efficient, which means your stroke volume is going to decrease. And if you decrease the stroke volume, you're holding all things else equivalent, decreasing the cardiac output. So we would not think that this is going to decrease or increase cardiac output. Okay. And generally, like I said, in these questions, there's only going to be one right answer. So if you do find the one right answer, and it's the right answer, then you can, by process of elimination, get rid of all the other ones, even if it's still a little ambiguous about which one it should be. All right, here is another way of looking at these natriuretic peptides. What do these things do again? they are going to cause fluid loss. And we're talking about fluid loss. And before I look at all the answer choices, I'm going to try and think to myself all the ways that fluid loss would affect the cardiovascular system. So fluid loss means that there's going to be a decreased venous return, again, for the very reason we just talked about. As the blood goes through the cardiovascular circuit when it's losing fluid, that means that there's a decrease in the venous return, right? Do you remember how a decrease in venous return will affect cardiac physiology? It decreases the stroke volume because it's actually going to decrease the end diastolic volume. It decreases how full the ventricle will be. And so this is going to be a decrease in cardiac output. So if we see one of these answer choices is decrease in cardiac output, then great, that's our answer. But when we look at that, oh shoot, decrease in cardiac output isn't one of our choices. So now we're left to try and find which one of these things is related to a decrease in cardiac output. Okay, and so we have to ask ourselves, why would the individual be decreasing the cardiac output? If the body is decreasing cardiac output, why is it doing that? And what is going on? And what's the condition that's requiring this this change in order to bring back homeostasis? And usually cardiac output doesn't necessarily have anything to do with blood pH. Now, I will say that if you have a low blood pH, your blood is acidic, it generally means that there's too much CO2 in the blood, and so your cardiac output is actually going to increase because you want to get more blood going to the lungs and back. But that's a little bit less of a direct relationship. So we might be tempted to think that A could perhaps be a possibility, but it's a little bit more ambiguous. And so let's take a look at some of these other ones. Okay, it could be high blood pressure or low blood pressure. And again, if we draw our vessel, again, if you've got this whole thing down pat, you should remember, that there's two ways to increase or decrease blood pressure. So anytime I see the word blood pressure, I'm usually going to draw a vessel like this and do, okay, you can either change the cardiac output, or you can change the size of the vessel. Either of those things are going to change blood pressure. And so we're told that we're decreasing the cardiac output. So you have to try and remember, okay, if I decrease how much flow is going into a vessel, how does that affect the blood pressure? So in these type of things, I usually imagine two scenarios. One where there's a vessel that has hardly any fluid in it, and there's the same size as a vessel that has tons of fluid in it. Which one would you think would have more pressure? And if the answer is the one with less fluid in it, okay, so keeping that in mind, all right, if I decrease the cardiac output, that should mean that I'm actually decreasing this blood pressure. Okay, so decreasing cardiac output usually indicates a decrease in blood pressure. So if the individual's body is trying to decrease blood pressure, does that mean that they have low blood pressure? No, because you wouldn't want to decrease your blood pressure if your blood pressure is already low, but you would want to decrease your blood pressure if your blood pressure was high. So now I'm thinking that C is the correct answer. You could make a case that perhaps A would be the answer, but it's not as direct as C, because cardiac output is going to have a direct consequence on the blood pressure, keeping all things equal. Okay, and then excessive vasodilation just for the sake of fun, let's think about what this would be leading to. Okay, if an individual had excessive vasodilation, we're talking about the size of a vessel. Basically, their vessel is huge. Okay, if somebody has their vessels way too big, that means that they probably actually have low blood pressure, because remember, increasing the size of a vessel is going to decrease the blood pressure in there. And so D and E are going to be kind of directly related. And so we already crossed this one out, and since this one's related, we can cross that one out as well. And then lastly here, this blood acidity. So, you know, on these regulatory mechanisms, we talked about both pH and blood pressure. And basically, when pH is elevated, what it means generally is that you have too much CO2 in the blood, or not enough oxygen. Okay, so a low pH, which means acidosis or too much acidity, is because there's a buildup of CO2 or not enough oxygen. The remedy for both of these conditions is to breathe more. Because every time you breathe, you get rid of CO2 and you take in O2, right? So if you've got too much CO2 and not enough oxygen, when you breathe more, you both get rid of the CO2 and gain more oxygen. So this is going to be one of the things that is going to happen when there's too much acidity. But another thing that's going to happen is there's going to be increased blood flow. That is to say, there's going to be an increase in cardiac output, because not only do you have to breathe more, you have to get blood to and from the lungs faster and more abundantly, right? So if we take a look, we're looking for any answer choice in which we have to breathe more, or increase cardiac output. Either of those things will help us bring the acidity down. And looking at all these choices, you can see that C is the most obvious candidate here. If we increase the respiratory rate, that's exactly what breathing more is. Okay, it means you're taking more breaths in a given in a minute, you know. So if this is a multiple choice, then I can go ahead and cross all these out without really thinking of them, and you should be set there. Okay, but just for fun, we can go through some of these. I think I might have goofed on this one, so there may be another correct answer. But okay, inhibition of the chemoreceptors. This wouldn't be the case because the chemoreceptors fire when they detect acidity levels rising, and we're told that the blood acidity is rising. Okay, there's elevated acidity. That means there's a decrease in the pH. Increased stimulation of the cardioacceleratory center, we would also think would be the case, because we want to increase cardiac output. And one of the ways to do that is to increase heart rate. Okay, decreased stimulation of the baroreceptors. Decreased stimulation of the baroreceptors. These baroreceptors stimulate when there is a high blood pressure, and so they generally, the effect of the baroreceptors stimulating is to both lower cardiac output and increase the size of a vessel by vasodilation, because both of those things are going to help to reduce blood pressure. So here's where you always have to be careful. If I'm decreasing the effect of that, you're basically saying that you're increasing, the net effect would be to increase the cardiac output or decrease the size and we said that this one here, increase in cardiac output, would be something that we'd want to do to help elevate that. So this is also true. And I guess now reading the question, it makes more sense because it's saying all of the following will occur except. So really the answer would be A, because this will occur to reduce blood acidity, this will occur to reduce blood acidity, and this will occur to reduce blood acidity. But we're being asked which one will not reduce blood acidity, and we already deduced that that would be inhibition of the chemoreceptors, because remember that chemoreceptors actually fire when the acidity raises. All right, hopefully that helps you get a little bit more practice thinking through the tangled webs of physiology, and I hope it's starting to become a little bit more clear for you. Let me know if you've got any questions.